The purpose of this video is to discuss the kind of electricity known as alternating current, or AC. At this point in your studies, you've worked quite a bit with another kind of current, DC, direct current. This is the type of electricity where current leaves the positive side of a battery, travels in one direction through a load, and then back to the negative side of the battery, delivering energy. If we were to look at the DC circuit we've seen up till now, we would see that we have a value of current that's fairly constant, assuming the load doesn't change, maybe with a slight downward slope for a battery, because batteries do eventually die and their potential difference becomes less. But over the useful lifetime of the battery, that relatively constant potential difference gives a relatively constant current. You've also studied quite a bit now about how we can use changing magnetic fields to cause electric currents due to the EMFs that are induced according to Faraday's law. You probably noticed that for generators, the type of current you have doesn't stay constant. It grows and shrinks and sometimes changes direction. So this is not a current just in one direction. This current alternates. So as I stick this in and out, I'm making the alternating current electricity back and forth. And I want to try to figure out why. One thing I hope you can see, and I'll replace this magnet with a picture I've made, is that as I move the magnet in and out of the coil, I'm changing the amount of magnetic field inside. Obviously, I can't put this in, but you can see at the pole, the magnetic field is the strongest, where the lines are closest together. So as I move that pole up and down, the amount of magnetic field enclosed by the coil is changing. So that goes back to Faraday's law. The faster I change the flux, the larger EMF or voltage I get, and therefore more currents. If I could suddenly make the coil much bigger while keeping the magnet in place, we would expect to see a current as well. If I could rotate the coil while keeping the magnet in place, we would expect to see a current as well. And in fact, that is something we can observe if we use the Earth's magnetic field. So I have a compass, and it shows that north, the Earth's magnetic field appears to be pointing away from the camera. And that means there's magnetic field lines passing through this loop. In other words, its magnetic flux at the moment due to the Earth's magnetic field is as large as possible. If I rotate it, now there's no flux because basically field lines that are pointing away from the camera can't pass through it anymore. But now it's at a maximum again. If I do this quickly enough, I should be able to see a current produced. So I have here a fairly ancient model. I think it might even be older than the school, but it's a really good model of how an electric generator works. This is the basis for how we generate electricity. We're going to see that it's going to convert the mechanical energy I put into it into electric current, which is what all generators do. There's a few basic parts to it. There's obviously the crank. There's a magnet. And the reason there's a coil of wire around that magnet is it actually can be an electromagnet that can make the magnet much stronger. Most important part, though, are these coils that can spin. And notice they spin between the poles of the magnet. We've talked about the idea of magnetic flux, and that's how much of the magnetic field is in the coils. And I think you could see when the coils are like this, the maximum amount of magnetic field can get through, because you can see the inside of the coil, kind of the donut hole. When it's like this, the minimum amount can get through, because that donut hole is facing away from the magnetic poles. So as I crank this, the flux will increase and decrease, and as we've seen, that generates an electric current. So I'm going to keep cranking always in the same direction. But watch the galvanometer. Something really interesting happens. it's alternating. It goes back, forth, back, forth. But I'm still cranking in the same direction. So what I'm making is an alternating current. So now you know part of the story. One of the reasons we have to know about alternating current is that for a lot of the electricity coming out of our walls, it was born alternating in a generator like you just saw. But that can't be the whole story. Every time we plug in a laptop, this device actually takes alternating current from our wall and turns it into the kind of direct current your computer needs to charge its battery or run its various computer chips and transistors. So we know how to convert between the two. At the end of the 19th century, there was actually a really serious fight between two great scientists. General Electric's Thomas Edison and Westinghouse Electric's Nikola Tesla. What won the day was something called the transformer. The transformer is a device that can change the potential difference of alternating currents, but not direct currents. And it turns out that the ability to change the potential difference in the conductors in a circuit is actually really, really important. So in this video, I want to talk about what a transformer is. I want to look at some equations on how we use the transformer. And then I want to talk about what the advantage of changing voltages is in wiring an electrical grid. At its most basic, a transformer consists of a metal rod, in this case iron, a coil of wire that comes in, and is hooked up to an alternating source. And then another coil of wire that's entirely insulated from it, but is wrapped around that same metal object. It turns out that even though there's no electrical connection between the two, you can actually make a light bulb light, or you can power a circuit using this arrangement. I'd like to show you this. So I'm going to use the DC lab power supply to show how a transformer works, and one of the issues with using the DC that Edison wanted to use. So I've got 5 volts on the lab power supply. I've got this old chair with steel legs. And to this coil of wire, I basically have the positive from the lab power supply hooked up, and I have the coil also hooked up to a knife switch so that we can turn off the electricity and turn it back on. There's plastic inside here. There's no electrical connection other than to the power supply and the switch. So we'll just slide that on. I got this other coil, and the only thing it's hooked up to is the voltmeter. So we'll slide that on. There's no electrical connection between these two coils. But I want you to see what happens when I turn the electricity in this coil on. We're going to see that it produces a measurable voltage in this coil, even though they're not connected. So here we go. Electricity. So you saw when I first turned it on, there was voltage. And when I turned it off, there's voltage again. But it stops pretty quickly. So on, there's some voltage, it goes away. Off, there's some voltage, it goes away. You probably recognize coils like this as being the same ones we used back when we studied magnetism. And we saw that in order to produce voltage in one of these coils, we had to move a magnet in and out. It couldn't just stand still, it had to be constantly changing. So right now, with no current inside the primary coil, there's no magnetic field inside the secondary coil, so we see nothing. If I change the magnetic field to non-zero by turning on the primary, we briefly, during the time of change, see electricity in the secondary. But then it goes back to 0 because it's not changing anymore. It's like you've shoved the magnet in and haven't pulled it out yet. Going back to non-zero briefly gives us electricity again, but then it goes away. So you'd have to keep turning this on and off. We have another way of continuously varying current, though, and that's alternating current. Let's look at an alternating current power supply. So I've got this hooked up to my AC power supply. It's wired to the yellow terminals. So what's going to happen when I turn this on, the coil to the right is going to have a changing current, creating a changing magnetic field. A changing magnetic field is going to extend into the coil on the left, which is then going to create a changing current. And the voltmeter should pick up that there's now an alternating current voltage. So I'm just going to go ahead and switch on. And we can see that we do indeed create a voltage. So that meter was measuring AC volts, alternating current volts. And that's kind of a mouthful. Before we get into what's happening, I do want to point out that the second coil, the one not hooked up to the power supply, is perfectly capable of lighting a bulb, and that bulb does not appear to change with respect to time. Just like the meter registering AC volts didn't appear to change with respect to time. But an oscilloscope tells a different story. The potential sometimes is positive and other times is negative. And what that really means is that the current sometimes is flowing into the white wire out of the yellow, and other times it's reversed. In fact, this bulb is turning on and off 60 times every second. And we can see that when we zoom into the millisecond range on this oscilloscope. So when we talk about alternating current electricity, it changes back and forth very quickly. Sometimes people think that it can't deliver energy because if the electrons flow one way and then the other, isn't that putting energy in and taking energy out? No, it is putting charge in and taking it out. But those charges are still delivering energy, and devices can use that energy as clearly this bulb is able to do. There's a few big ideas about transformers that we have to mention. The first is they're a trade-off between voltage and current. So you probably remember voltage when I was throwing the ping pong balls at this board. Voltage is the energy a charge carries. So when I was throwing those ping pong balls, it represented how hard each ball was hitting the board. Current represents how many balls you get per second, or how many charges you get per second. They're not really what matters when it comes to electricity. What's really important is power. How much energy are you delivering per second? And a transformer doesn't create energy. So the key thing about it is that the power going in has to be equal to the power going out. Now we know the equation for power is current times voltage. So that means the current in times the voltage in has to be the current out times the voltage out. So really what we're talking about here is conservation of energy. If basically the same amount of energy is going into and out of the transformer every second, that means the product of voltage and current must be constant on both sides. Just some vocabulary, we typically call the side hooked up to the power supply the primary coil, and the one not hooked up to the power supply the secondary. And this really shows us how we can change potential difference across the transformer. We can have a small voltage on one side and a large current. In other words, each charge is not carrying that much energy, but charges are flowing very frequently. On the other side, we can have the same rate of energy by having few charges flowing, but each charge carrying a lot of energy. So, in other words, we get to pick our voltage. Just some other important equations. We can determine what voltage you get in the secondary coil versus the primary coil by comparing the number of turns of wire. In this equation, the voltage in the primary divided by the number of turns in the primary equals the voltage in the secondary divided by the number of turns in the secondary. This helps you figure out what voltage you'll be getting out of the transformer. If you have fewer turns in the secondary than you do in the primary, you're going to step down and have a lower voltage. If you have more in the secondary, you're going to step up and have a larger voltage. One other thing, the average voltage in AC is 0 because it's varying between a peak and a valley, and basically there are 60 complete waves every second. So we have to find some other way to measure magnitude. This black sine wave here represents what power looks like in North America. The brown one sort of represents what it looks like in Europe and the UK. And we use this thing called the RMS value, root mean squared value. You'll learn about RMS values in another class, but they're related to the peak voltage according to this equation. But they're a good measure of the relative size of the potential differences, even though the average potential difference across all times is 0. This is a set of transformer coils made by Pasco Physics, and what's important about them is that they differ in number of turns by a factor of 2. So the yellow one, which we're going to use as our primary, it has 400, and you can see we have one that has half of that, one that has twice of that, 4 times that, and 8 times that. So we're going to see how this transformer transforms an input voltage of 3. So in all these photos, the primary will be the left side, and it has an input voltage of 3, like this meter shows. So here we have 2 identical coils. They're not connected, so the magnetic flux coming out of this coil is what's causing a voltage in the other coil. Since these are the same coils, we'd expect them to get roughly the same voltage. 3 divided by 400 should be equal to 3 divided by 400. We lose a little bit because the transfer is not 100% efficient here. We still have a primary voltage of 3 here, but we have 800 turns or twice as much over here. So if you solve that transformer equation, you should get twice as much voltage, or 6. You can see we're roughly in that ballpark. Again, there are some losses. This coil has 1600 turns, or 4 times the input, so we expect 4 times the voltage. That would be 12. Again, we're pretty close. We are losing some. Here's what 8 times as many turns looks like. We expect 24. Transformers also can be used to lower voltages. So this blue coil has half as many turns as our input coil. So we'd expect our 3 volts to drop to 1.5. It drops to about 1. So all that's left at this point is to discuss why it's so important to be able to change voltage, and why transformers are such an important part of our power distribution system. Sometimes it seems obvious. Your power supplies have a certain voltage. In North America, we have an RMS AC voltage of between 110 and 120 volts. This clock here, this silver one, comes from the UK. That's its plug. And it's expecting an RMS AC voltage between 220 and 240. So to make it work right, I had to step up the North American power to give it the higher voltage it wanted. Here's a quick look at the math, kind of the power equals power equation. We can see on the primary side we have 120 volts. That means we're going to have a relatively large current, because on the secondary side we have 240 volts, which means we'll have a relatively small current. I didn't know exactly how many turns are in that transformer, but when we do the turn equation, we can see there must be a 1 to 2 ratio between the primary and secondary in order to get the voltage to step up. We'll practice problems like that. We'll also revisit the clock because we've been talking a lot about the y-axis of this graph, the magnitude of the RMS voltages. We haven't talked a lot about the x-axis, how frequently the voltage switches. So we'll use these clocks to study the importance of that. So that's a useful discussion about how we can change voltages if we need to. But it doesn't answer the question of why we even have different voltages. Why would we want a big V or a small v? Turns out that the economic importance of that question cannot be overstated. If we take Ohm's law and plug it into P equals IV, we get the equation P equals I squared R. The rate at which energy is dissipated as heat depends on current and resistance. Or in other words, anything that has resistance, if you pass a current through it, is going to create heat. And the bigger the current, there's a quadratic relationship between how quickly it dissipates heat. We've talked about this equation as the reason why we need circuit breakers. If that heat's dissipated in your house walls, it could burn your house down. But for the power company, if you are spending money heating up your power lines, that's money that you're not able to get back. It's just wasted. So the power company wants to avoid high currents at all costs. So given the choice, they would pick high voltages. But Ohm's law explains to us why in a lot of places we can't have high voltages. If you have a large potential difference V, you could end up getting a very big current if you put anything across that potential difference by accident that has resistance. If you accidentally touch two wires that are thousands of volts, you're dead. You're going to get a big current through you. So it's not safe to have big voltages around. So it would be really nice to be able to choose. In places where we want to transmit lots and lots of power and we don't want to waste money or energy, it would be nice to have large voltages, hundreds of thousands of volts, and relatively low currents. In places where people are going to access that power, we can put up with the loss of energy as heat because it means we can have the safer lower voltages. So every power plant births its energy at a certain potential difference. A transformer steps it up to hundreds of thousands of volts to send through high tension power lines. And then on its way to you, it passes through various substations. Here's probably the last transformer before your house, these little cylindrical things on poles. Here's one outside one of our schools, which is a little bit different. But at the end of the day, this is how we can transmit power without wasting lots of energy. Thomas Edison really didn't like this because he had a patent to transmit power using direct current. Not being able to change the voltage, that meant that there had to be a power station almost in every neighborhood. It wasn't practical. And that's why we adopted Tesla and Westinghouse's alternating current electrical system. So, at the end of the day, I hope you now understand the beauty of the transformer. We'll practice using these equations, and we're going to learn a lot more about alternating current because it's a fascinating topic.